Thanks for the introduction. And at least I'm glad to meet with your group virtually. Hopefully one day, once the pandemic abates, we'll be able to shake our hands without any worries about virus spread. But today, I'm representing the Apache Ignite community, as Haim said. Also, I'm working for GridGain, that one of the companies that builds and contributes to Ignite. But today, that would be a little bit more generic talk. We are going to spend next, I think, 40 or 50 minutes talking about the memory computing essentials. These days, guys, and like we joined this like 15 minutes ago, SF kind of asked me and Nicholas, like, how do you compare Ignite? How do you compare Hazelcast? Like, what's the difference? How the products are used? And usually you have these questions because the market, the technological landscape of different memory technologies is broad. These days we have caches, such as Redis or Memcached. We have products like Ignite or Hazelcast. We have in-memory classical in-memory databases, such as MemSQL or VolDB. And all those products and technologies have various capabilities, some of the unique features, but at the same time, there is something fundamental that characterizes every technology, something essential that can be said about, let's say, Redis, Ignite, or Hazelcast. And today we are going to talk about those essentials, some of the basic design principles, so some of the basic capabilities that you should keep in mind. Because once you, let's say, decide to use any in-memory computing technology for your project, then you would select one of the projects from a category you need, but at least with the help of the essentials in mind, you will be able to understand how those products are designed and work, what are the most obvious or basic optimizations you can undertake, and how you can speed up and start working with your in-memory computing software as quick as possible and with a few hiccups. So a little bit about myself. So why actually I came up with this talk and we have this conversation today. I've been working with distributed memory systems for the last 5 years. I'm gaining my practical experience by contributing to the Apache Ignite project. That's a distributed database that is used for in-memory speed and scale. And also I'm being paid, I work for GridGain, that's the company that donated Apache Ignite, as we calculated 6 years ago, to the Apache Software Foundation. And as a head of developer relation, I have a privilege, working with many developers and architects who are designing and using not only Ignite, but other distributed systems for various projects and business problems. Before that, before the distributed memory systems, I used to work for Oracle. I belonged to the Java engineering and architecture group. I was contributing and developing Java for for mobile devices, for embedded devices. If you remember the time before Android took over the world, Java was you might have found Java on many mobile devices. And actually, there was a special Java Micro Edition product that was installed in Sony Ericsson, Nokia, and many other handsets. And I was among a few who were developing that version of Java. And then, like my last time at Oracle, I was developing Java for embedded devices that are running on microcontrollers on different CPUs. What's interesting was about that work and that we were tasked, to put the whole Java virtual machine and run it on a device that has just 1 megabyte of RAM, and you are given just 1 megabyte of RAM and do whatever you can to prepare an image of your Java virtual machine so that it can fit in that memory and also leave enough space of RAM for the applications that would be running on the same device. And my professional career, why Oracle, why Java? My professional career studied at Sun Microsystems at the Technology Evangelism Group. I was bragging about and spreading the word about not only about Java, but about NetBeans, Solaris, and many other nice technologies that were developed and created by Sun Microsystems. Talking about the agenda. So we'll start with the introduction. I'll try to I'll show why in-memory computing matters, why eventually I created this talk and we have this meeting today. Then I will spend like 2 or 3 minutes briefly introducing you to the Apache Ignite. I'm doing that only because I'm selected Ignite, obviously, for the sake of the presentation. Along the presentation, when we will be covering all these essentials that you see down below, such as data partitioning, affinity collocation, or collocated computations, I want to show you some, demos, code, how this feature works and how to use it. And I will be using Apache Ignite. But at the same time, as I said previously, most of these essentials are used by any, let's say, by most of the memory computing technologies, meaning that once you learn about the data partitioning, you will understand how data is scaled and distributed, not only in Ignite, but let's say Redis or MemSQL. When it comes to the affinity collocation, that's also one of the crucial optimizations that you need to keep in mind so that you can run efficient like SQL or complex calculations. And that's, again, that exists in Ignite, and I will be showing you demos and code samples, but also it's supported by other in-memory products, which is good for you, right? And also, I have opened the chat window, so we don't need to wait till the end. After every section, like once we finish with the data partitioning, I will deliberately take a pause and I will check if you have any questions. So don't hesitate to put the questions in the chat window and go unmute if you want to talk anything out with me just verbally. So let's go. Let's start with this obvious question: why in-memory computing, and why do we even care about this talk today? Generally, all the in-memory computing technologies and memory caches and memory databases, they were created to give us speed and scale. Let's figure out the scale question first. If you look at let's say Redis, Memcached, or Apache Ignite, MemSQL, those technologies are distributed, and they were created distributed from the get-go, which means that if you have, let's say, a 3-node cluster that keeps your data, your application would connect to this cluster, and for that application, that cluster would be just one single entity it will be working with. And scalability is horizontal, meaning that, let's say right now the capacity of this cluster is no longer enough to fit all your data set. So what do? You just scale out your cluster. You are adding extra 2 nodes so that you can keep, let's say, a half a terabyte of data instead of 100 gigabytes of data. Then another thing can happen. Right now, probably you can fit all the data in memory across these 5 machines, but you are seeing that you are running out of CPUs. Your CPUs are oversaturated, and you are not able to complete all the operations in a performant way. So again, you can go ahead and for the sake of performance, you can keep scaling out your cluster. So that's the horizontal scalability. And how is it different from, let's say, classic single node databases like relational ones? With relational databases, at least like, let's say, with some classic version of MySQL or Postgres, usually if you want to scale, you have to upgrade to a more powerful machine that goes with more CPUs and with much more disk space or memory, which implies that you might have a downtime, right? At least minimal downtime. With in-memory systems that are by design distributed, you usually scale out. Whenever you need more space or whenever you need more CPUs, you're just adding more nodes to the cluster. That's about the scale. And when it comes to the speed, we all can we understand that memory is much faster than disk. And but how much faster is it? I like this table. Actually, that's not my invention. I found it on the internet. Some smart guy decided, to give an example of different system events that every CPU have to execute and process. And then those events you can see in the first column of this table. And then he decided to scale the actual latency time that it takes for a CPU to complete any operation to the left to the scaled latency. And what's the scaled latency? That's the latency of our human universe. We live in the world where we measure the time in seconds, minutes, days, months, or years, right? We all understand that nanoseconds, microseconds, and milliseconds are extremely low and small units. But for us humans, like physically, it's kind of hard to kind of comprehend the difference, how big is the difference between like microseconds and milliseconds. But at the same time, we can clearly see and even sense the difference between minutes and hours, because like we understand like for how long a minute lasts or an hour lasts. And that's what we have in the final column. And right now, if we, let's say, pay attention to these three columns that show the latency difference between main memory access and disk access, it's like the difference between minutes and days in our human universe. And that's why in-memory software is gaining so much popularity these days. Because yes, we all understand that the memory is fast. It's like the difference, the latency difference or the speed difference is like the difference between minutes and days. And it's not surprising then if you deploy, let's say, Redis as a cache, or if you deploy Ignite as a database, you will get performance advantages. But at the same time, it doesn't mean that everything will be given to you for free, meaning that it's not enough, just to go ahead and deploy a distributed memory cluster and achieve nirvana, as I would say, because you need to keep in mind some of the design specificities of those distributed systems. You need to know some basic optimizations. You need to understand how you would migrate your applications that were, let's say, running on relational databases to your new distributed memory systems. And that's why we have this conversation about essentials today. As I said, Apache Ignite, I selected Ignite as a reference platform to demonstrate all those essentials in practice. So give me 3 or 5 minutes to introduce you to this project really quick. From the features perspective,
Dennis, one question. You said the RAM speed is the main point here, but it's not really RAM because most of the access would happen over the network, right? So which is the last row in the table you showed. Isn't that the decisive factor in the speed?
Yep, and that's why we are talking about the essentials. Okay. Because once you understand like what the data partitioning is, you will see how different requests are routed across your cluster. Because sometimes you just need to go to one of the cluster nodes, and that would be just one network round trip. You still have the same network round trip if your application goes to relational database, right? And when you're running, let's say, a more complicated queries like SQL with join, when obviously you need to join the data that is scattered across your cluster nodes. Again, you can use, you need to keep in mind optimizations, like not even optimizations, design practices such as affinity collocation. I will cover it in this presentation.
Okay.
Today. Yes, and the point of this conversation, and that's a great question. I did not stress it out really well because, yeah, many wrongly assume that once you deploy your cluster, you will be gaining all those benefits. That's not true in most of the use cases, because you need to kind of design your applications properly, and you need to know how the system operates internally. Because that happened to me many times. Let's say when we are getting a lot of questions on the Ignite user list. And sometimes you see the question like a guy says, oh, I was comparing, I was doing a performance test. I was comparing, let's say, Ignite to Postgres. And for some reason, like Ignite, why Ignite performs much worse than Postgres? And then you started digging what he's doing. And sometimes people just, don't understand how to use this thing, because it's not that obvious.
Just one small comment. I think network today in the same data center is a much higher figure, which competes with memory. It's not like a rotational disk or a one connection.
Mm-hmm. So, that's right. That's right. All right, and returning to Apache Ignite, I think that you've all read this feature set. you see that there are many capabilities, but I define two primary capabilities of Ignite. First, it goes with the distributed storage. And second, on top of the storage, Ignite provides a variety of APIs so that you can get and process your data. As a storage, by definition, Ignite keeps data in memory, obviously, and it can persist all your data on disk. When it comes to disks, Ignite can, there are two options. It can persist your changes in an external database, or it can keep it in its own native persistence. And I will show you the difference between those two configuration modes on the next slide. On top of that storage engine, let's say you deployed Ignite cluster, you loaded data, Ignite with data. So what's next? You can use SQL, you can run transactions, you can run key value operations, a lot of different capabilities. Today I will be using, for the sake of demonstration, I will be using SQL, compute, grid, and certainly we would be running a distributed Ignite cluster. Everything you see in the middle, in red, belongs to the Apache Software Foundation, fully free, can be used by anybody. And to the left, to the right, in blue boxes, that's what GridGain adds to Ignite on top in its own enterprise versions. Things like backups, security, management and monitoring, so on and so forth. When we're talking about Ignite use cases, because like as a platform or as a database, Ignite goes with many capabilities. And I would say that I saw even exotic usages of Ignite, but what are the typical one? What are the epitome of Ignite use cases? The first one is Ignite as a cache. Still, many start with Ignite using it as a basic cache, but the cache that supports standard SQL capabilities, the cache where you can transact on, like running distributed transactions, and the cache where you can, over which you can run your Java computations. That's, for instance, how Ignite as a cache is different from Redis as a cache. And also Ignite is one of the dominating use cases is Ignite as a database. In this case, nothing changes from the API standpoint. You still would be keeping data in memory. You would be using SQL, transactions, and whatsoever. But when it comes to the persistence, you will persist all the data in Ignite native persistence. In this way, with that persistence, what are the benefits? First, you no longer need to keep all the data in memory. Depending, let's say, on your data type, you can keep operational data and historical data in the same cluster. Your operational data can fully reside in memory because probably you access it frequently, while for historical data, most of it can sit on disk. And when you will be using, let's say, any SQL command of Ignite, Ignite will join all the records, those that are in memory and those that are on disk. That's on Ignite. And also, once you enable that persistence, 100% of the data will be on disk, and then as much as we can, Ignite will be caching in memory. But once your cluster gets restarted, you don't need to wait while your memory gets warmed up. Ignite will be serving all the data from disk, which means that if for any reason you need to restart your cluster or your cluster went down, because let's say your data center, the electricity in data center is off, once you are up and running, once the cluster is up and running, the data will be served from disk. You're not waiting while the memory gets warmed up. From the Apache Software Foundation, we have already touched point on that. Ignite belongs to, Ignite is one of the more than 350 projects, top-level projects of the Apache Software Foundation. It's if to talk about their activity, that's the third most active project on their user list. So what's the user list at Apache? That's actually the place where you usually come and ask questions to the community of developers of Ignite. And we are just, behind Flink and Lucene, but we are getting much more activity than Kafka or Apache Tomcat. All right, enough about Ignite. And right now, let's do this. Let's start an Ignite cluster first. Let's do a small pause. I'll start an Ignite cluster first so that it's ready for the rest of my experiments. And after that, we will switch to the first essential capability, data partitioning. And with data partitioning, as you will see, that's actually the essential of essentials. It explains us how distributed systems, such as in memory, caches, and databases, scatter our records and how our requests get routed. But in the meantime, let's do this. I have my I've already downloaded an Apache Ignite distribution, and I will be using my personal laptop for today's presentation. I'm locating in the bin folder that goes with some scripts. And right now, let me use this command. I'm using Ignite SH script to start a node of Ignite. And that's the configuration. There is nothing specific in this configuration, just some network settings. If you're interested, I can show it to you later. But there is nothing that worth our attention. All right, let me go the full screen. So what happened? Ignite node is started. We have two types of nodes. That's the server node. The server node, that's a JVM process actually that is running on my machine. Ignite, like let's say Cassandra or like Hazelcast, Ignite is a Java middleware. So when we are talking about Ignite as a database, or when we are kind of talking about Ignite cluster, that's actually a cluster of JVM processes that are interconnected over the network. And what I'm doing right now, I've just started my first server node that will be keeping my data on my local laptop. At the same time, if I want to start another node, let me execute the same command in a different tab. I will be using two node cluster. You can see that two nodes are interconnected. So right now my cluster is comprised of two nodes. Everything is running on my local laptop. And that's how many CPUs the whole cluster has. That's how much of heap memory is allocated for my Ignite cluster. In the heap memory, we keep all the data and indexes. And Java heap is still used for your objects. Whenever you will be querying your Ignite cluster, Ignite will be using Java heap for temporary objects. That would be garbage collected once, let's say, your request is processed. If the cluster is running, and also throughout this presentation, I would be using this management tool. It's called GridGain Web Console. That's a legacy tool GridGain has, but it serves me well for this presentation. If I go here, let me go to the dashboards. This tool I'm using a hosted version of this tool that is deployed somewhere on Google Compute Engine. And this tool is already connected to my two-node cluster that is running on my local laptop. I don't have, let's say, any caches or tables created so far, and we will do this a little bit later. But that's it. I've started my cluster. I have two nodes running, and we are ready for the experiments. So let's proceed with data partitioning. So with data partitioning, actually, that's the feature or the capability that enables horizontal scalability for all the distributed systems, not only in memory systems, but when you're talking about Cassandra or MongoDB, they also have partitioning or like sharding. For me, sharding and partitioning is like, I would say it's all the same. So what's the purpose of data partitioning? Let's say that you have a relational database. And with relational database that is running on a single machine, you keep all your records in the same place. And that is great, right? Because once your query comes to this database, the data will be served from disk or like from in-memory caches really quick. But at the same time, sometimes it's expensive or impossible to have all the data, to fit all the data on a single machine. That's why we are talking about distributed systems and databases. And once you deploy a distributed cluster, like a 3-node cluster of Ignite or like Redis or anything else, then internally, the database or cache will be using the partitioning algorithm to take and distribute all your records evenly across your allocated nodes and resources. In my today presentation, I will be using the world database schema. That's actually the one that is created for MySQL database, and I adapted it for the SQL syntax of Ignite. So I will have country table, all the countries of the world. We have city tables. Every city is located in one of the countries. And also we kind of, I'm not using the table country language, but it exists. Actually, it tracks all the languages every country speaks. Partitioning. So let's do this. Let's assume that we have this partitioning algorithm that does all this black magic for us. But what we as application developers and architects should do to ensure the data gets distributed evenly across the cluster. What we like, and luckily, all we need to do, like by default with the partitioning, is just to create our caches and tables. What you see on this slide, I'm creating the country table, and that's all I need to do as an application developer. I just execute this command. It's familiar, it's simple. Once this command gets processed by Ignite or other distributed system, the table will be created, and the table will be split into a fixed number of partitions. We would have partition 0, 1, 2, like 5, up to some maximum number. In Apache Ignite, we have, like by default, 1024 partitions. Like Hazelcast might have a different number. And usually this number is always configurable. It's easy to do. After that, you have this table, you have these partitions that are actually logical. And then the goal of the partitioning algorithm is to distribute those partitions across your current cluster. So it might happen that partition 0 and 1024 will go to the first node. Like the other partitions will be also distributed using some algorithm that is supported by your cache or database. And again, all we need to do is just to create this table by default. You can override the number of partitions if you need, but usually you don't do this. And once you created this table, the rest, like what you see to the right of this slide, like all the partitions are created by the database, by the partitioning algorithm, and then the same partitions are distributed across the cluster. And what's next? Let's say we created this table, and the next obvious step is to put some data inside of this cluster, right? And again, we as developers, we just need to execute familiar commands, such as insert into country, like insert this record of the United States into my country table. And that's it. That's all I do. And what happens internally, what the partitioning algorithm does. The partitioning algorithm will take the value of our primary key and will map this value to the partition number, to one of the partitions. And once the partition for your specific key and record is identified, this partition will be mapped to one of the nodes, because every partition is stored on one of the nodes of your cluster. And let's assume that in this case, the primary key of the country table is the code column. And what the partitioning algorithm does, it will take the code value, it will calculate the hash code of this primary key. Then by using this hash code, it will kind of map this hash code to one of the partitions. In this example, I'm just assuming that this record has to reside in partition number 5. And right now, the partitioning algorithm, the cluster knows that partition 5 is on this third node. That's why this record will be pushed and added to this cluster node. Simple, right? And that's actually all you need to know about the data partitioning. That's the most fundamental thing that makes distributed databases like these databases or in-memory databases so lucrative from the scalability perspective. You're just starting your cluster, you're giving, that much disk, that much space, and that's it. The rest is on the database. They have partitioning or sharding algorithms that will be distributing our records. And let's say if to answer one of the questions SF asked me before, like, let's say we have network. All these nodes obviously are interconnected over the network. And right now, let's say that I inserted this record, the record of the United States in the cluster. And if my application wants to read it back, then it would be using, let's say, select star from the country where code is equal to USA. This query will be routed to one of the nodes. It will not be broadcasted because the primary key, because you're trying to select a record using the primary key, and internally, our SQL engine will take this primary key, calculate the partition number, and will send this query to one of the nodes. And when you are running thousands or hundreds of such queries, when you're selecting records of Canada, Israel, Russia, France, etc., all those queries most likely will be routed and served by different nodes, which is good for us. So let's take a pause here once again, and I will show you how that looks like from the practical perspective. As I said, we are using this country or world database. So let's try to load this database in our cluster, and let's see how the partitioning algorithm automatically distributes our records. Okay, inside of Ignite, let me show you when you can Ignite supports. Today, I'm mostly will be using SQL capabilities, but also you can use key value APIs, so transactions, etc. And when it comes to the SQL, Ignite supplies you with JDBC and ODBC drivers. I will be using one of the tools, SQLite, that is developed. That's an open source tool that you can use for, let's say, any relational database or any database that provides a JDBC connectivity. And I will be using this tool to connect to my locally running Ignite cluster. So what I'm doing here, I'm just connecting, I'm using Ignite, this Ignite JDBC driver, and I'm saying that my Ignite cluster is running my local laptop. It's all clear, right? Okay, I'm connected to the cluster. Let me run this tables command. That's the command that is supported by SQLite tool. That's not something that is provided by Ignite. I don't have any tables, but I have this project prepared. That's my SQL script. That would create the country table, that would create city table, and then it would populate this whole database with some sample records. And I want to load the script into my Ignite database. To do that, let me recall this. Yeah, that's the command. It's cached. So generally, I'm using this command of SQLite, and that's the location of this script. Let's do this. The data is being loaded. And let's jump back to the monitoring tool. So here is, if I scroll down, now I would see that we've created these 3 tables. In Ignite, we also use the term caches. So what's the difference? Because I'm referring to tables during my presentations, but also if anybody of you are familiar with Ignite, we also use caches. For me, it's all the same. You usually use caches when your application utilizes key value APIs such as cache get or cache put requests. But when you're primarily using SQL interface of Ignite, then you usually talk about table. Usually cache and table, it's all the same in Ignite, no difference. So that's the city table is created that we have just 4,000 cities, a few countries, and some data in the country language table. We were talking about partitioning, right? And we were talking about partitions. So right now I'm interested in how Ignite distributed my records, because all I've done, I just connected to Ignite with this JDBC driver and I loaded my database. But what happened internally? Internally, all the tables were created, they were split into their partitions, and then those partitions somehow were distributed across the cluster. With this tool, I can do this. Let me select this city table and open this partitions view. So here, as you can see, that we have on the first node stores 516 partitions. The other node stores 508 partitions. That's how the partitioning algorithm of Ignite decided to distribute these partitions. And next, with this table, I can see how many records or how many keys are stored in every partition. Let's do this. Let's sort by partition number. You can see that, let's do this. Yep, you can see that some partitions are on node 1, some partitions are on node 2, and in some places, in some partition I have 3 records, in the other partitions I have 4 records. So generally, that's how this distribution works. Usually, you should not expect that the distribution would be like 50-50 precise, meaning that if you have 2 nodes, then like 50% of the data precisely would be on one machine and the other 50 on the other machine. Usually that's not the case. Usually all the partitioning algorithms, they do all their best to achieve this even distribution, but they also cannot sacrifice the performance. That's why we usually say that it's almost evenly distributed. And that's actually what you see with this Ignite example. Like 560 partitions are on the first node and the rest are on the second node. And then the keys are mapped to the partitions, and you can see how many keys are located in every partition. So that's the partitioning. It's all simple, right? Here is why I wanted to start with this, because once you know the partitioning, once you know how the data is distributed, you basically realize how the horizontal scalability works, how the data gets distributed, and what to expect from your distributed in-memory system. Any questions, guys?
What hashing function is being used in order to spread it?
In Ignite, I would say that in Ignite we use rendezvous hashing. That's probably you heard about it. But also we see that the two most famous and most widely used algorithms are consistent hashing. Cassandra, for instance, implements consistent hashing, and rendezvous hashing. We in Ignite use rendezvous hashing. So that's all the algorithms have their pros and cons. If you want to read more, I can probably at the end of this talk and can give you a nice article that explains more details on this rendezvous hashing and consistent hashing. Just please remind me. All right, I see that there is another question. What happens when you have a unique constraint? Are all partitions accessed? When it comes to the unique constraint, when it comes to Ignite, we do not support unique constraints. It's not implemented, at least yet. I don't remember what are the plans of the community to support it. But if to talk about other distributed in-memory systems, for instance, MemSQL or VolDB, they support unique constraints. And yes, usually with unique constraints, as long as you have to support uniqueness, it will affect your performance. If you, let's say you have 3 nodes and you need to ensure that one of the records, that a record you insert in your cluster is unique, a key is unique, then you would need to broadcast, let's say, to all those nodes. But that's, let's say, if that's not your primary key. If you're talking about primary keys, the primary key in Ignite or in any other memory database is mapped to one of the nodes. In Ignite, we do not send any exception. Usually, if you're trying to insert, if you will be trying to insert, if you're inserting the same, if you're inserting a key that is already in your cluster, then you will get an exception saying that this key already exists. So for the primary keys, the uniqueness is already supported out of the box. But if you're dealing with secondary keys, then that's not supported in Ignite. I know that some of the databases like MemSQL support it, but for secondary keys, usually you need to kind of at least to communicate with more than one node to ensure that uniqueness. Hope my answer makes sense to you. What happens when you don't query by the primary key? And that's actually the next chapter. We will be talking about the Affinity collocation, where we will be reviewing more advanced queries like SQL with joins. Just wait for a couple of more minutes. And there is another question. If you allow persistence, can it grow beyond memory size? Yes, in Ignite, that's the case. And in Ignite, it's not just a backup copy of your memory. It will keep all the data on disk, and then depending on how much memory you have, Ignite will kind of try to use all of your memory space. But yeah, you can easily grow beyond your memory regions. Another question, don't you spend a lot of time to reduce records from different partitions? Let's say to select some where, yeah, let's say that's SQL is a huge topic. So I would say that when you're trying to calculate an average or sum, or then more than one node would be involved. And in this case, let me move ahead with the next chapter with Affinity collocation, because it should give you a hint and answer to all those advanced questions that you're starting to ask. So let's continue with the essentials or with the Affinity collocation. and then I will return to your questions. All right, affinity collocation. So you've seen that actually with data partitioning, it's all wonderful, it's all great. I just deployed my cluster. It took me just 1 minute, and all the data is distributed. So what can go wrong? Because certainly something will go wrong if you're not prepared. Let's take this example. So let's kind of change our situation. In the previous example, I was talking about a single table, about the country table. But let's say I have two tables. I have country table and I have city table. For both tables, our partitioning algorithm will be doing all its best to distribute records like some way or another. And when it comes, let's say, to the city table, let's say I have the record of Canada and France that are stored in the country table, and they are located on different nodes. But then when it comes to the cities, that's what happened. I see that a couple of Canadian cities, Toronto and Calgary, are stored together on the same machine where I keep the primary record of my Canada as a country. But Montreal and Ottawa are stored on a different machine. And the same I can say about cities of France. I have Paris, I have Marseille. Marseille is stored on the same node where I have the record of France, but Paris is on a different node. And the warning sign here suggests that that's not a kind of critical error. It's not the end of the world. That might be a totally correct situation for your use case. If you're, let's say, running basic key value operations, if all your operation does, let's say, if your application just caches all the records in memory, like cities or countries, and all it does is, just selecting of those records using key value APIs, like cache get, like get me this record of city, like return me the record of Paris, then you don't need to do anything else. You just, trust this partitioning algorithm that will distribute records somehow. But once you decide to execute more complicated queries, such as this one that returns the most populated cities across Canada and France, you would inevitably hit the join phase. And what happens with joins? And so here is I will be talking about Ignite. And usually this feature is available in all those distributed memory systems that provide you with SQL interfaces. So what happens here? Let's dig deeper. First, your application initiates this query. And this query, as long as that's a complex query, that's not a query when you're using the primary key, this query would be broadcasted to your cluster nodes. When it comes to the cluster nodes, your cluster nodes will start executing it. And once they come to this join phase, they will figure out that some of the data is missing locally. And those two nodes will start interacting over the network, shuffling data. Like let's say the node that stores the Canada record, it needs the records of Ottawa and Montreal, and it will request those records from the second node. And that would move the records from one node to another. And network, as you guys, some of you properly pointed out in the very beginning, is expensive. In this example, I'm just showing how 3 records are shuffled over the network. But imagine that you're running your SQL with join, or you're doing aggregate query over, let's say, hundreds of thousands of records. And you need to move, or if you need to move all those hundreds of thousands of records during the join phase, that would be an overkill for your in-memory system. You can easily and quickly lose all the benefits of your, shiny and bright in-memory cluster. Why so that? Let's return to this table that we used before when we were comparing, the latency of memory and disk. But right now, pay attention to network. Network, it's like the difference, like the speed difference between, let's say, disk and network is like the difference between months and days, or sorry, month and years. And that's why it's important, to keep in mind at least affinity collocation is one of the obvious optimizations and design practices for your distributed and memory systems. Because uh, if you would have a lot of operations or queries that involve this data shuffling, like people can start you questioning why you even selected this memory system when all the data is being moved over the network and you just, I don't see any performance benefits. But as long as we have, all these capabilities like SQL with joins, not only in Ignite, but let's say MemSQL, or like we have a lot of distributed databases such as Google Spanner that are distributed and support SQL. It means that there is a way how you can make even joins performant over your distributed records. And in Ignite, we call this collocation, data collocation. If to come up with some more generic term, I would say that just grouping your data, grouping your related data. In the relational world, we're using foreign keys as a data integrity measure. In Ignite or distributed systems, we use Affinity keys to group together our related records. So for that query that I've shown you before, my ideal distribution would be as follows. I want all the Canadian cities to be placed on the same cluster node. Because I'm joining those records, I'm frequently going to join country and city tables. And that's what I want to achieve. And the question, how do I get to this point? Again, as an application developer, all I need to do is just, I need to know first, as like step 0, I need to know my business model. I need to know the relation between my tables, between my objects. And once you identify that relation, you need to set up an affinity key. So what we have here, I have the country table. And for that country table, the primary key is code, the code column. And when I will be creating my city table, the primary key of the city table would be a compound key. We will be using the ID of the city itself for uniqueness. And also we would be using the country code. So generally, that's how a record is identified, a city record, by ID and country code. And the purpose of the affinity key that I also have to add to enable that distribution I've shown you on the previous slide is to instruct my partitioning algorithm that when my application will be inserting the city records, you, the partitioning algorithm, have to use the value of the country code for the, let's say, to calculate a partition and to calculate a target node. And it's not surprising that as long as all the cities that are located in the same country have the same value for the country code, all of them will be located on the same cluster machine. And all we need to do is just to define this affinity key. And after that, when you will insert the city, and I will show you this in a couple of minutes, all the cities will end up on the same cluster node, and we will actually get this distribution. That's all we need to do. Once you do this, and if you execute the same query over the same cluster, but over the cluster where the data is collocated or grouped together, then you would not have that data shuffling phase. Your query arrives to both cluster nodes, and it joins all the records over the locally available data, and you're getting a correct result back to your application. All right, let me check the questions first, and then I will show you, as always, a demo how this affinity collocation works and how we can set up it in practice. So the question is, what about affinity key skewing? Data distribution is not balanced equally between nodes. Yeah, that's the data skew is an interesting topic. Just what you're actually saying is that let's say, let's assume that we are comparing Canada and we're comparing France here, right? Let's say in Canada, you might have 200 cities. In France, we might have like 150 cities. And that's the skew, right? But the assumption is that each node will store small countries as well as big countries, which means that statistically, we will end up having, let's say, like United States or Canada might be stored on different node. And also small countries like Cuba or anything else will be located on across both nodes as well. So this skew, data skew, can be avoided by the partitioning itself. That's like one of the things that usually happens. If it's inevitable, then you can define you can go deeper and you can actually use special configuration settings, kind of saying that if that's the key, let's say I have New York, and in New York, we have how many, like 10 or like 20 million people living in New York. And if I cannot keep all the data on the same node, then I can say that, oh, let's say I have New York and I have, let's say, London, and I don't want those two big cities, data of those two big cities to be stored on the same node, then I can actually go and instruct, use special configuration or create some custom logic that would instruct my cluster, the partitioning algorithm, to never ever place those two big records data, like those two big groups of data on the same node. Also, what we were doing, for instance, I was involved in one of the projects, credit card authorization. Whenever you're paying with your credit card, they have, to check your transaction over the latest transactions you had, like over the history of the latest transactions. And usually those systems store not only the history of your transactions, but they also store the history of the merchant transactions. Let's say you are an Amazon or you are Walmart, and usually you probably do like thousands, if not millions, transactions in days. And it's not even possible to keep all those transactions on a single machine. And even with that distributed world, you cannot keep all the history of Amazon in a single partition. And with Ignite, what we were doing, we created a special logic that was injected in the partitioning algorithm of Ignite that would actually split. You have partition, and in every partition, we would store no more than, let's say, 100,000, 100,000 records. Once you put 100,000 records on the first partition, our logic for the partitioning algorithm would use another partition to keep the rest of their Amazon data, and that would go on. That's what we used. But that's a kind of a positive thing, that you don't need to do this. Usually, you don't need to do this. In my practice, we had, to come up with those advanced partitioning schemes only, like 3 or 5 times, and those were massive, like projects that, keep petabytes of data. But usually it will be handled by the partitioning algorithm, and usually you would not notice any data skew. Who is the thick client? One of the Ignite nodes getting the query, the GBC driver, really client. So here is, like thick client. I should have updated this slide. Think about an application, just to make this conversation generic. It can be Ignite, or it can be any other distributed in-memory database that supports SQL. That's your application that is connected using a JDBC driver or EBC driver or a thick client. In Ignite, the thick client is just, Java APIs. We just call it this way. That's a client. That's your gateway. That's how you connect from your client application to your cluster of server nodes. Just don't pay attention to this. Just an application. Okay, let me show you an example. I have this cluster running, and now I have some of the queries predefined. I go to the SQL tab. I have some of the tables here. That's the table I'm looking for. So let's warm up first. With this query, I am just returning the most populated countries in the world. And here is, I am just querying one table. There is no any join yet. And that's the answer. China, India, United States are the most populated. I'm not sure that the numbers are actual. As I said, I just used this database was created for my SQL users, and I just reuse it for Apache Ignite. The license permits me to do so. And when it comes to the more advanced query, that a little bit, like that's actually the query I was showing you on the slide, but it's a bit more modified. So here is, I'm querying the top 3 cities across the following countries. So let's run this query over my 2-node cluster. As always, I'm getting some exception. Let me execute this query. Yeah, that's one of, I think that's an issue of this tool, some bug of Web Console. But anyway, that's the answer I received from my cluster. But I would say that that's not a proper answer. That's a wrong result. In Ignite, by default, this data shuffling is prohibited, meaning that by default, whenever you are running a query with join, the nodes will not be shuffling data between each other, meaning that you can get an incorrect result set. Kind of the current logic is that I can say that I agree with that logic, but Ignite requires you as an application developer to tell him that, all right, you know that the data is not collocated. So you tried probably to collocate it, but it's not possible to collocate it. That's why please allow the data shuffling, because I were not able to collocate. Let's say that we were not able to collocate these records. We just created these tables and we inserted these countries and cities the way it was on one of the opening slides. And right now I'm telling Ignite by checking this parameter, allow non-collocated joins. So basically I'm saying that if a node detects that data is missing locally, the nodes let the nodes to shuffle the data. Let's execute this query. You see that it takes more time to complete this query, like 2 seconds. But that's the right answer. Seoul, São Paulo, and Shanghai are the 3 most inhabited cities across these countries. And it takes more time, right? 2 seconds versus milliseconds, because some of the data was shuffled, even on my local laptop. So how can we fix it? We know that there is some obvious relation between countries and cities. So let's define affinity keys. For that, I'm going to this script that I used before. And here is, if you remember my slide, I need to change the primary key and set the affinity key for my city table. So as I said, we are going to use country code. The country code would be a part of the primary key. And then I need to define the affinity key, country code. That's it. And once I create these tables, once these cities will be inserted, the partitioning algorithm of Ignite would be using the value of the country code to calculate the partition number for every record and then a destination node. And as I said, it's not surprising that as long as all the cities, that are located in the same country have the same value of the country code, they would be placed on the same cluster node. That's the goal. So I need to recreate this table. For the sake of simplicity, I would recreate the entire database because I changed the partitioning scheme. I have to do this. I have to recreate the table. So the table is recreated. Just in case, let me refresh the screen of this tool, because I cannot, just to ensure that the new database is loaded. Okay, so I no longer need this. I'm telling Ignite that all that data shuffling is prohibited for this query, no any data shuffling, because I know that the data is collocated. So let's execute. You see, I am executing Seoul, São Paulo, Shanghai. It takes like 10 milliseconds versus 2 seconds that we had with data shuffling. And that's it. Like with the affinity collocation, that's one of the essential things that characterizes not only Ignite, but many other distributed memory systems. And keep it in mind, whether you're selecting Ignite or whether you're selecting Hazelcast, MemSQL, or Redis, whatever, keep in mind that you are better to define and to review whether that affinity collocation exists. Because from the performance standpoint, it's stark, right? It's great that we have data shuffling options, because sometimes you cannot logically collocate the records, which means that for some of the queries, you would have the data shuffling. But your goal is to minimize a number of those queries when the data would be shuffled. Most of your queries, set a goal for yourself. If you're running some computations or queries, 95% of my operations I want to be running in this collocated fashion, so that minimal network usage, because network is expensive, right? And you've seen even with this trivial example. But that's it. That's how you can quickly, update this table, reload this table, and right now, versus instead of seconds, we are getting into milliseconds range.
Dennis,
Uh-huh.
a quick question. What happens if you need to repartition when you already have, like this situation when you have it, when the system is already deployed? Is there a practice on how to repartition the data?
I would say that what the users of Ignite do usually, if they don't want to introduce any downtime, right, or like they usually create a second table, and they move a copy of the data to that second table using a special tool. And after that, they switch all the queries to that second table. And with that second table, you kind of changed, in that second table, you changed your partitioning distribution approach. Probably you changed your primary key. That's what actually I've done. But yep, it's you have at least the brute, like the most obvious solution is just you have to create a new table and then switch all the operations to that new table once it's preloaded, and then remove the old table. That's what most of the developers do.
And then you need to change the name of the table, or there is aliasing or something like that that can solve that.
Yep, that's actually a good question. I think that if I'm not mistaken, in Ignite we have aliases, if I'm not mistaken, but memSQL definitely does this, like aliases. Yep, that's a good point. I think that yes, with aliases, that's what you would do.
Thank you.
Let me see. There are some other questions from Nicholas. There is no dynamic rebalancing across nodes.
Well, you answered, you just add like another table and okay. So yeah, there is dynamic rebalancing, but you answered how you can cope with that. Thanks.
All right. I got it. Yep, thanks. Another question, why not adding new nodes? We can add a new node whenever we want. If you want, we can do this, and the data will be actually redistributed. We can do this experiment if you like. But probably you're asking this question for something else. Please explain, Amir, or just unmute and...
I'm asking with regard to the question about repartitioning. So instead of repartitioning, let's add new nodes. It will achieve the same effect, isn't it?
The problem with like repartitioning, that's a good point. I would say that we have some of the users that would imply advanced optimizations for the partitioning schemes in such a way that they would have a dedicated server machines that would store particular partitions. In this case, obviously, like in this case, you just, when you're recreating something, you can create a special machine for one of the sets of the partitions and then kind of switch everything. That's possible, but that's like advanced, and that would require you to do a lot of testing because that's not provided out of the box in Ignite, which means that you have to test that thoroughly to ensure that nothing breaks. But if to talk about these tables, when I'm talking about like every table consists of, like in Ignite, like consists of 1024 partitions, and those partitions are scattered across the nodes, which means that it's kind of hard. If I'm redefining this if I'm redefining a primary key, that's what I've done for this table, which means that all the partitions can be redistributed, which means that anyway it will affect all the nodes, because this country table, the data of the country table is across all the nodes. Unless you decide, let's say, to put a single table, the whole data, all the partitions of a single table on one of the nodes, then yes, your optimizations would make sense. But by default, and that's easy to maintain and easy to use, all the data is just across all the nodes. And then if you need to do this, just you are creating a table, and as someone suggested, sorry, I did not remember the name, you can use aliases if those are supported, just not to update your application code frequently. All right, folks. Let's quickly. I think that we are almost done. It took more time, but it's good that we have this conversation right now, because I don't like to put off all the questions till the end. And the last section, collocated computations. So let's recap. So what we've learned so far. We know that data partitioning does all the black magic by spreading all our records over the network. But then, we know that default distribution is ideal for simple queries like cache get lookups. Think about Redis. Redis is designed as a wonderful and fast, high performance cache. And usually when we work with Redis, we use like primary key lookups. And that's when it's more than enough to have data partitioning. But once we are stepping on the territory of complex queries, like the example of SQL with joins, we need to have something more advanced, because data can be shuffled. And when we are shuffling data, we are diminishing performance benefits of our in-memory computing cluster. That's why we can apply different optimizations and design techniques such as affinity collocation. We call that Affinity Collocation Ignite, let's say in MemSQL or Oracle, how it's called, scale out timestamp database. They use a different name, but primarily it doesn't matter how it's named. The goal is just to group related data. And with collocated computations, I want to talk about another thing that exists, that is available for you as Java developers. And I believe that most of you are already familiar with this technique, especially if you have ever used Hadoop, like MapReduce APIs of Hadoop, or if you have ever created or launched any Apache Spark calculations. So the idea of the collocated computation is that you have your Java logic that is multi-step. It can be complex operation that involves several round trips between your application and your distributed cluster. And instead of, let's say, executing that logic in this classic way, when the logic is executed on your application and the logic reads, let's say, a lot of records, does something with those records, writes something back, reads another records, you can take and execute that logic on your cluster nodes, right on your cluster nodes, all other locally available data. And that's actually what Hadoop does, right? Like with MapReduce, the first versions of MapReduce, you just create your task. And what we see on this slide, you execute this task on your application. Then the second step, this task gets executed across all your cluster nodes or a subset of the nodes. You decide where you'd like the task to be executed. And then if those server nodes, if the task needs to return anything to your application, a result is returned from every node, and your application can execute the reduce phase, and that's it. That's what you can do. And the same, and this actually capability, like in the relational world, usually we use stored procedures, but with stored procedures, unfortunately, we are restricted in terms of the capabilities, what we can do. With Java, as Java developers, you can use, let's say, any API like GDK or any custom library, and to execute that logic on your cluster machines. That's actually supported by many Java databases like Ignite or like Hazelcast support this. I think Gigaspaces or Gemfire is in memory, as examples of the in-memory databases. They also support this capability. Let me give you a really, just here is, I found that it's always nice to talk about real examples. And I can tell you my story, the story I was involved in. That happened, like 3 or 4 years ago when those were the times when I kind of were wearing many hats, and I was helping one of our biggest customers, like of Ignite and GridGain, to switch to, let's say, to accelerate and to switch from a relational database. And that's a bank. That's one of the biggest banks. They store millions and millions of different savings accounts. So actually you can, like, as with any basic bank, you can open a savings account, you can put your data, you can put your money in, and once a month, the bank would apply some interest rate. So eventually you would get some money accumulated over there. And as any bank, this bank had this standard operation. Every month, the bank would start a special application. That application would connect to their relational database. It would read all their kind of, how many millions, like 10 or 20 millions, if not more, like I would say dozens of millions of savings accounts from the database to the application. Then they would use some financial libraries written in Java to do some calculations. And eventually at the end of that calculation, they would apply the final interest rate to my account, to your account, to everybody else's account. And all those millions accounts then would be written back over the network to your relational database. And with that database, it was taking them around, let's say, 2 hours and 20 minutes to complete this whole business operation, calculation of their interest rate for all the millions of accounts. And that was not the problem of that relational database. The relational database is fast. It's extremely fast. The problem was the network. They were moving all the records, millions of records from the database, from the application. They tried to use stored procedures, but that was not just impossible. They had those financial libraries that were written in Java, and they like were Java developers. They wanted to use Java. That's why they kind of agreed with the business management that, all right, every month, late night, when the load on the system is minimal, I kind of would launch this application, and that application would calculate everything. So what happened with Ignite? Let's talk about Ignite. When they switched to Ignite, like they also decided to, let's talk about Ignite. They also decided first, they preloaded all the data, all those millions accounts in their memory cluster. And then in that logic, they just updated, they switched to Ignite SQL, from that relational database SQL to Ignite SQL. And but again, the logic was executed in the same manner. The application would connect with the Ignite cluster, would read from the Ignite cluster all the data from memory, which is faster, and then would write all the data back to Ignite in memory, which is faster than to disk. And they've got a bit of performance improvement. The logic was executing, let's say, for like, it was taking them 1 hour, like, and 50 minutes versus 2 hours and 20 minutes. Like, it was like, they got an extra 30 minutes. It was executed on 30 minutes faster just because the data was residing in memory. But that was not a breakthrough still, right? It was taking like more than an hour to complete this calculation. And then we advised, like, guys, let's go ahead and let's actually take this logic that is running on your application side and let's execute it on their cluster nodes. They collocated all the records because they had like all those millions accounts. For all those millions accounts, they had some information related to their account, like payments, etc. And everything was collocated. Let's say all my financial information for my account was stored on one of the nodes, and that was done for all the other accounts. And then when they were executing this logic in this compute fashion, they reduced the calculation time to 14 minutes, like from 2 hours, 20 minutes to 14 minutes, just because they eliminated this heavy usage of network. That's it. And the summary of the story, like why I'm telling you this story, because like when you will be switching to any, let's say, distributed in-memory system, it can be Ignite, it can be anything else, it doesn't matter. If that system provides an ability to run your Java computations, take advantage of it whenever it's possible. Because let's say if data is collocated, just run that calculation over your cluster of nodes. You will be using all the resources of your cluster, and you would be minimizing the usage of your network, because network is the evil for distributed systems. But if you know how to, restrain that evil, if you know how to minimize the usage of network, you are the king. You will be able to kind of take tremendous advantages of your distributed memory cluster. Example, before we will do the summary, we will recap. but I want to show you how actually how practically those computations look like, because that's a Java user group. We are talking about Java. And I prepared some of the examples for you. I will be using the same cluster, but here is what are the samples I have. Bear with me. Collocated, like for instance, yeah, this one. Yeah, let's take this one. That's what happens here. Oh, let me shut my window. It's too bright. So here is, I'm connecting to my Ignite cluster that is running locally. That's a Java application, by the way, right? Just main, function, etc. That's the configuration. I used the same configuration for my server nodes, and I promised to show it to you. Let me show it to you. Here is I'm just defining some of the network settings. So I'm just telling my application and my server nodes that the whole cluster is running on my local laptop. That's why that's the network address. That's how the nodes will auto-discover each other. And here is I'm just saying that every node that will be started, every server node cannot use more than 800 megabytes of RAM on my personal laptop. That's what I do. Nothing, that worth our attention. Simple configuration. So that application would connect, and then that application would run several calculations. So the first computation, this actually computation, let me see, that's the function. So we are getting inside. We are using Ignite compute interface. And then I'm using this Affinity run. Affinity run assumes that I want this logic, that's my logic, to be executed on the node that stores like this record. That's, if you remember, that's my primary key. Country and city is the primary key of my city table. And here is like my Affinity key. I want to execute this logic. Once this logic would be executed on the server, I will be iterating over all the countries that are stored on this server node. And then for every country, I would be just, calculating the total number, like a total number of the cities stored on this node. And I'm saying that that's just local SQL query, no need to make it distributed. And then I'm actually not even returning anything, right? I'm just executing that on the server nodes, and that's it. It's, just something artificial. The goal is just to show you that you can basically run whatever you want. It can be broadcast query, or it can be Affinity query. With the Affinity query, again, you're just telling on which node you'd like to execute it. And then, so this part, like this whole part, will be executed on my server nodes, while this is executed on my application. So let's run my application. Okay, it's building, it's compiling. Okay, it's ready. So the application says that it's over. Something has calculated. So let's jump here. Here is the output of my first server node. This server node received this request. It was calculating for what? For Canada. We were calculating the total number of cities in Canada, and that's what was printed by this server node. And the second query also went to that node as well, right? So actually, the second node was not calculating anything in this example. But you always can do a broadcast query. In that broadcast query, you let me show you this simple logic. In this example, again, my application connects to their cluster, and I'm executing this function. What this function does, it broadcasts this logic to all the nodes. And every node, once this node receives this logic, it needs to deserialize the class and print this message. And that's another logic. Again, this logic arrives to my two cluster nodes, and every cluster node needs to return all these details about its local environment. Let's quickly run this example. Okay, so here as we see that the application executed this logic, and it's got some response from my server nodes. When I go to the server nodes, let's see, that's the hello message. that everybody received. And the second node received this broadcast message as well. So that's what you can do. Just, basically any logic. And what's interesting here is that, let's say that my cluster is already running, but my application is dynamic, right? When it comes to our database or distributed database or cache, ideally, we don't want to disrupt it. We don't want to restart it frequently, right? Because that's the place where we keep our data, and that's the database which our applications depend on. But our application logic can change frequently. Let's say that I decided to change this logic. Hello node. Probably I even decided to create, some class, private static class. Let's see, person, age, string name. It's like I want to update my logic. So, and what happens? Like, do I need to restart my cluster, or like everything will be handled automatically? Okay, I'm creating this, and let's implement the toString method. Okay, done. And let's say that some logic, I'm updating this logic, my task, okay, age 40, Sam. And I can update it here. And what happens now? I'm just restarting. I don't need this. That's another function. Let me just re-execute this query, this application, and we'll see what happens. So the computation executed successfully. If you go here, you can see that both nodes received and executed this updated version of the logic. So what happened? I was not updating the class path of this nodes. This node is a separate Java process that is running on my machine. And interestingly, when, at least with Ignite, when you execute a computation like this one, the request internally, an internal request arrives from this application to your server or your server nodes. The server nodes are receiving in that request the name of your class or your anonymous function or your Lambda function. And then the server nodes will try to locate this class in their local class path. They will fail to locate this logic in their local class path because it's obviously missing. It exists only on my cluster node, on my application side. And the server nodes will request my application saying that, all right, we don't have this logic, please send us the bytecode. And the application would sends the bytecode of this logic over the network to your cluster nodes. Once the cluster nodes receive the bytecode, they are able to deserialize your class and they will start executing it. So with this example, they would receive the bytecode for this Ignite runnable, which is an anonymous function. Once they start executing the code, they will get to this class and they will not be able to find this newly created class in their class path as well. And this whole process will be repeated. They would request the bytecode for this class from the application, and the application will respond. And that's actually how we were able to achieve this. So the beauty of this approach is that your cluster, your distributed cluster is running, your database is working and operating. And whenever you need to update your logic, let's say that calculates savings accounts, or your logic that probably prepares your personalized screen for Netflix, you don't need to restart your cluster. Just forget about your cluster. Just update your logic, update your application, restart your application, and then re-execute everything. The cluster will be able to figure out that the bytecode, the class version of your logic has changed, and it will reload everything, the new bytecode from your server. And that's good for us, right? Okay, as a summary, let me do the summary and then I'll switch to your questions. I see that we are getting a lot of the questions in the chat window. And the summary I would use, I would use this picture, because the goal of this presentation was not to pitch you Ignite, not to pitch you in memory computing technologies. One of the idea why I decided to create with this topic is because I spent a lot of my time, at least before, working with architects, consultants, and developers who were using not only Ignite but other distributed systems, and many of them wrongly assume that it's just enough, to start a distributed memory cluster and get all those exciting benefits that, let's say, a marketing team of a vendor kind of tells us, right? But in fact, it's not enough just to put all the data in memory and achieve nirvana. You already, like, throughout this short conversation, you've seen that, yes, with data partitioning, the basics of the basics, it's all simple. The data gets distributed. But once you start running and creating operations that are close to your production ones, you will see that you need to use Affinity collocation. You want to minimize network usage. Sometimes even when you collocate all the records and your joins execute fast, but if those joins are just a part of a more complicated multi-step calculation, still you would be utilizing network, and the network is evil. That's why how you can end up using collocated processing. So that's why keep all those essentials in mind. And then regardless of the memory technology you select, most likely this whole fundamental knowledge will help you to to do all the required setup beforehand, to design your data properly, and to move your applications, let's say, from the relational world to the in-memory world, or to combine your in-memory world with the relational world with your applications. So thanks. And let's check the questions. The questions, the first one is, there is any restriction on dependencies? Yeah, the question is related to the compute logic. As for the dependencies, I'm giving the following advice. Let's say that inside of your logic, you are using some frameworks, such as Spring or Hibernate. And usually, my suggestion would be to have those frameworks added to the class path of your server nodes, so that when the data, the bytecode get transferred from your application to your servers, we don't need to transfer the bytecode of your frameworks. Because first, sometimes it's impossible. Some of the classes of your frameworks might not be possible to serialize and deserialize. And second of all, is just, too overwhelming for, to move like all that logic mainly dependencies. So I would say that not any restrictions on dependencies in particular, but it's like more of frameworks or big libraries, add them to the class path of your server. While your custom logic, it's up to you. Your classes just need to be serializable. The other question sounds a bit like a security issue someone could exploit. Is there any authentication? Yep, let's with compute. Actually, that's a wonderful conversation. 1 week ago, I spoke to one of the database administrators who is managing Ignite, and he said that his Java developers and architects came to him asking, like, all right, now just set up a cluster for us, and we want to like do this and that. And the guy was concerned about, let's say, security, because like he said that, oh, sure, my dear developers are excited about, let's say, Ignite, because it gives them all the possibilities they want. They can run any random code. And then he was asking about, let's say, authorization, authentication. In Ignite, we have something basic. In GridGain, we provide a kind of special security framework, which you can use, let's say, to decide who is allowed to run a computation, what is allowed to do with that computation. In the latest versions of Apache Ignite 2.9, the community members integrated these compute APIs with Java, like with GDK security framework, meaning that you can tell, for instance, if you're running your computation and you don't want that computation to create any file on your file system, right, or to open any network connection, it will be possible to configure that, because Ignite will be using security APIs of the GDK. So it exists. I mean, but you need to see like what's available in Ignite and what's available in GridGain and what's available in both. So, and question from Nicholas, for this reason in Hazelcast, you need to set the server class path when it starts different approaches. I think that you're talking about those frameworks, right, and libraries.
I know it was about, yeah, like dynamic sending bytecodes to the server. Like, yeah, in Hazelcast, it's not dynamic. You need to set it once and for all. I mean, I have a different opinion on puts the libraries of big frameworks on the server path. I would really, really encourage you to have the data that is on the server side, like completely unrelated, agnostic to any framework. I mean, the code that runs on the server, it should be agnostic. It should be your pure business logic, and to design your application like that. I mean, I wouldn't advise you to put Spring or whatever, Hibernate on the server class path, but that's my opinion.
Yeah, I think it would depend, and it would depend on the situation, because sometimes it's just in my practice it was obviously application developers would like to make it, as you're saying, everything is flexible and agnostic as possible, meaning that we have our database, right, and we have, let's say, our application. But sometimes it was that they're just trying to run their computation and the computation fails on the server side because some of the classes of the frameworks or libraries are not possible to deserialize. And then they were required to add those to the class path of the service. Or probably, you might be talking about some other approach. For instance, I know that it's possible to, let's say, you don't need to add those classes to the class path of the servers, nor to the class path of your applications, but you have, as you're saying, right, a server or special place where you can load those libraries from, right? Is this what you're talking about?
No, I'm just telling, yeah, the computation, the codes that runs computation server side should be like agnostic to any big library. So you don't need to set it on the class path of the server at all. I mean, again, that's not developer point of view, that's architect point of view. Yeah, because if you allow developers to do that, then in the end, you will find yourself with a big class path on the server side.
Yeah, another downside, it's always a trade-off. Another downside of this approach would be, let's say, if you put a lot of libraries to the class path of your servers, then one day or another you would need to update those libraries, meaning that you would need you would need to restart your servers. It can be done in a rolling upgrade fashion, like one by one, so that your cluster is not down entirely. But anyway, that's one of the implications of trade-off. And like while talking to you, that's actually I remembered another approach. We worked with one of the big high-tech companies, and they actually have this use case when they need to run a lot of computations over a distributed cluster, and they don't want to have the libraries on the application end, and they're not ready to add those libraries to the server side. Like that's what you're advising not to do. At least in Ignite, we have a special API. It's called like deployment API, which means that your jar files can be loaded from any random, let's say, place, like a network drive. And in that configuration, when, let's say, they run any computation, application executes this computation. Computation arrives to a server node. The server node does not find it locally in the local class path, and the server node is not loading it from the application, but it will load it, the jar from, let's say, from that network drive. That's also one of the, and in this probably that's kind of might be an ideal solution for architects who still want to have, some flexibility in terms of their jars loading, but they don't want to put a lot of garbage into the class path of their server nodes. That's what Nicholas discouraging you from doing.
I think Nicholas is pointing out to keep the data layer clean and not polluted with various zoo of classes coming there. If you're, especially if you're doing it in batch, you would be inclined to use, say, Spark, where it is a zoo for all those jars that they get dispatched, but they never sit next to the data really.
Mm-hmm. All right. That's right. Okay, so let me stop sharing. And I see another question. How big does it grow number of nodes data? For example, bigger systems, I think that you're asking about Ignite. So in Ignite, we have, I would say that I have to talk about the largest deployments. Like Microsoft uses, like they're running for Ignite clusters, and each cluster goes with, let's say, 300 or 400 nodes. So in total, they have like around 1,500 nodes. That cluster doesn't keep a lot of the data. I cannot disclose the numbers, but they use so many nodes for their calculation purposes. They need a lot of CPUs. Those clusters are used by Microsoft Azure infrastructure. They have a special security service that tracks all the activity in Azure, not like all the applications, but some of those applications that enable that module. And they are capturing all those events, analyzing them, and they need that cluster. That's, I would say, one of the like 400 node clusters each. As for the biggest in terms of the data, we have many banks like companies. They store terabytes of data. Some of them are approaching the petabytes size. And in that case, the cluster sometimes doesn't need to be measured in thousands of nodes. For instance, one of the bank, every individual node has around a terabyte of data, like 700 gigabytes of memory on a single node, and they're just running, let's say, how many, like 20, like 30 or 40 machines, and anyway, you're getting a kind of a cluster of, let's say, 30 or 40 nodes, but with a massive capacity in terms of the memory and CPUs. So the other question, can Ignite guarantee consistency, or it's mostly used as a cache? Ignite supports distributed transactions, ACID transactions, so that can span multiple tables, partitions across multiple nodes. But for those, it's not supported for SQL APIs yet. It's supported for the key value operations. So with distributed transactions, you have to know your primary keys, so for your records. But then once you use the primary keys, you're good to go. You can run across many caches, many tables, across cluster of nodes. I assume there is also control of application factor. How does it cope with the fault? Yep, you can have, and usually that's the best practice. At least you need to have at least one backup copy of your data. In today's presentation, I was showing just, like every node, there is just only one copy of the partition. But if you want, let me quickly share back my, but yeah, doesn't matter. You can increase that replication factor. It's just a setting in your configuration. And the other, how does it cope with fault cap theorem? So here is you need, I would say that it's either consistency or availability. When it comes to the partitioning out of the box in Ignite, you have some of the interfaces that you would need to implement if you want to survive and kind of deal with split brain scenarios. In GridGain, there are a bit more advanced things, but I would say that out of the box right now, there is no any sophisticated out of the box feature for the split brain. But that's actually what community, what Ignite community is working on in the next version of Ignite 3.0. The community is planning to introduce, not planning, just the community has already started working on a sort of consensus protocol. So in addition, like to these transactions, for those who worry about split brain, the consensus protocol will be introduced in Ignite in version 3.0.
So today, when you have replication, all the replicas are equal. It's not that one is primary and the others are replica copies.
In this, let's take two nodes, like my example. When you have two replicas, I mean, let's say you created, you increase your replication factor, which means that my record is let's say my bank account record is stored in the primary copy of partition, like partition 10, and also the same copy of my record is stored in the backup copy of this partition 10. So the partitions are here, like here is on the first node, I have the primary copy, here is the secondary copy. When you would be requesting my record, the request would come to the primary copy. When it comes to the synchronization, you can have a full sync synchronization between these two copies. If you update my bank account, then the request can come to this node, and that node will not commit the change until the change is successfully committed to this backup copy. Or you can relax this consistency, it's up to you for the sake of performance. But at the same time, you would have, let's say, partition 15 or partition 50 that stores, let's say, your record. And the primary copy of that record will be on this node, while that node will be keeping a backup copy, which means that actually from the partition's point of view, there is a primary copy of a partition and like one or more backup copies of the same partition. But from the node's standpoint, there is no any notion of backup or like replica. All the nodes are both primary and backup, because some of the partitions are primary, some of the partitions are backup, and the same applies to the other node. That's how it works in Ignite.
Promotion from secondary to primary on fault?
The partitioning algorithm, there is a process called rebalancing. So what happens, let's say, yeah.
Before the rebalancing, just the detection of a fault and when is the promotion happening?
It's handled. It's, let's say, if even with this two node scenario, if one of the nodes goes down, you still have a full copy of your data because the other node stored all the backup copies for like of that node. Usually, but if we take a 3-node use case, 3 nodes, and one node is down, then backup copies, let's take partition 10. And the primary copy of partition 10 with my bank account was on this 3rd node. The 3rd node is down, and I know that the backup copy of that partition is stored on the 1st node. So that backup copy would be promoted to the primary one so that the cluster can continue serving my request to that partition, to my bank account. But right after that, another backup copy of that partition with my record would be created on the 2nd node. And the rebalancing algorithm will kick off. It will copy the data from this just promoted partition 10 from the 1st node to the backup partition on the 2nd node. And that happens in background. Yeah, if you're interested, yeah, I can put together some of the, or you can find me. Let's say you can email me at dmagda@apache.org if you need any pointers or references. I can give you a lot of documentation references or articles that explain how this all works in details. Do you have any other questions, my friends?
I have just one question. I read in the documentation that the implementation for the SQL interface is done using an embedded H2.
Mm-hmm.
So wondering how, I mean, when you run a query, so obviously the part that is running locally on each node is can be run as a smaller query, so to speak, on the H2. which does most of the logic for you. But was just wondering, how did Apache Ignite implement the reduce for the query engine, not the compute, for just the query engine itself?
Mm-hmm. Yep, that's right. We use the H2 database engine, but we use it only for the during the execution planning phase. I mean, we do not store any records or indexes in H2. It's just, optimizer of H2 and execution planner.
Ah, okay.
That's
okay.
it. And what happens when you start your, actually, how much time do we have, folks? If you have 5 minutes, I have a couple of advanced slides that I can use to show you how H2 is integrated. Do I have 5 minutes?
No. Sure, no problem.
Yeah, give me. I will show you, because generally every node is running, every Java process, like these two nodes I have on my laptop, they are running an instance of H2 locally, but they use only their execution planner, and the same for the application. And a part of your question was how this whole thing works in a distributed fashion, because from the Ignite standpoint, we had to couple together H2 and make this. Our Ignite SQL engine is distributed, which means that we do care about fault tolerance, queries routing, reduce, and map. Okay, I'm looking for the slides. Give me a second. It should be here. Okay. Bear with me. Okay, this should be this. Yep, that's what I'm looking for. All right, I need to share the screen. Okay, and we are switching here. So that's actually what I was saying. When you're starting an Ignite node, you have that H2 logic running inside of your process. But all the data, all the indexes are stored in Apache Ignite. Also, that's changing right now. We are integrating with Apache Calcite SQL engine. In the coming future, we would have 2 engines running, so that you would be able to select either H2 or Calcite for your queries manually. And then probably we would end up having only just Calcite if we will be satisfied about that query engine. But anyway, whether that's H2 or Calcite, it's pretty much all the same. We are just using those engines for the execution planning and queries optimization. And then let's say that you want to execute this query like this one. Select average population from the city. So what happens? On your application again, so here is, let me just rename that to avoid confusion. That's your application that is connecting using Ignite thin client, or like JDBC driver, doesn't matter. That application will send this query, as long as that's the average, it will broadcast it to your nodes that store the city records. And then on those nodes, that query will be kind of transformed into the following one. Select some population, some 0, count from the city. And it will be executed on these 2 nodes. Once every node finishes its execution, it will respond to your application, and then the application will execute this query locally, executing this reduce phase. If anything happens, let's say during this query execution, if this node fails, the Ignite SQL engine will detect this, and it will decide, does this node have all the data needed to complete your query properly? If it doesn't, you would get an exception saying that I'm missing some data because just data loss, we don't have all the partitions. If, let's say, that node has all the data locally, then this query will be, let's say, probably re-executed to ensure that you are getting everything back. And what else? What else? I think that, yeah, from the memory perspective, yeah, the memory is kind of, let's say, we are using our off-heap memory, as I said. Ignite keeps all the data in off-heap, and that off-heap memory is split into pages. We have data pages with your records. We have index pages. With those index pages, we use B plus tree. So whenever you query Ignite using a primary key or a secondary key, all the lookups go through the B plus tree indexes first. And then once your value key is found, you would go and read a record from a particular data page. And when it comes to the Dudi, you probably were asking about like persistence, like what if I cannot keep all the data in memory? Let's say that's the example actually. For instance, here as you see the memory, data page 5 and 2 are in memory, cached. We can read it from memory as fast as possible, but page 0, 1, etc., they are only on disk, which means that when your application, whether you're using SQL or whether you're using key-value, if the data that is sitting in page 0 is not in memory, Ignite will load this page from disk in memory, and if there is not enough space, like here, it will remove, let's say, any other page from here to free up some space.
So Ignite is managing its buffers, and it's not based on memory mapping in OS.
You can, yep. So that's our own memory. Like, that's our own storage engine. That's how like our storage engine we are used and we are selected for in memory use cases. But anyway, you can turn us into a classic distributed database with persistence. We use memory mapped files for write-ahead logs. You know, like not here. We don't use memory map files here. That's our own storage engine behavior. But let me see. I don't have. But yeah, like with classic databases, when you are writing, when you're doing any change in your cluster, and if you have Ignite disk tier enabled persistence, then we are not trying to update these pages first because that would become like expensive. We are writing your update to a write-ahead log file of your node. And then like over the time, we are kicking off checkpointing process. It's like in Postgres or any other databases when dirty pages in memory will be synced up to your disk, and then you can trim the size of your write-ahead log file. That's how we work.
So the persistent format, if you do, let's say, a lot of writes and then you delete the records, etc., is there any garbage collection kind of maintenance needed on the persistent files, or how is it? Is it log structured? Is it B-tree on the files itself? If you can shed a bit more light on it. I hope I'm not drilling too deep.
It's a B-tree. It's a B-tree storage type. It's a B-tree. So then it's like classic, nothing. The only difference is that that's a distributed B-tree.
Yeah.
But it has all the advantages and disadvantages of those B-tree storage systems.
Yeah.
I would say then it means from the use cases perspective, the ideal use cases are mixed use cases when you have, let's say, the same like amount of reads and writes, or reads intensive. When it comes to writes, if you're dealing with writes mostly, then probably you should be looking at LSM storages, like, or like Cassandra, like if it
you
makes
pay
sense.
penalty on the balancing of the B-trees.
Yep. As for that, if you even want to learn more, probably just write to me and I can give you some advanced materials that our contributors, those who are contributing to the storage engine, they are creating public pages for the rest of the Ignite community who are also coming and contributing. I can give you some pointers.
But the natural spot is read intensive, right?
And read is excellent for caching use cases, and read and mixed, let's say, when you are doing a lot of, like, let's say, almost the same amount of reads and writes. That's always the case. As for the write intensive, I did not see actually a lot. Usually if you write, you also read a lot. It's kind of intertwined. Okay, let me see if I have any other questions really quick. The chat window disappeared. No, that's it. Oops, stop sharing. So, anything else? Do you wanna? Are you curious about anything else? If not, then
Thank you very much.
Yep. Thanks a lot. Thanks a lot for inviting me. Hope it was instrumental and fruitful for you. And again, as I said, my goal was not just to pitch you Ignite. Certainly, I would be happy if you select and use Ignite. But the goal of this presentation material was, just to share our experience and my experience on what are the most something generic. What are the generic and essential capabilities across, if not every in-memory product, but at least most of them, so that you are equipped with that knowledge when you are deploying your first in-memory systems.
Thanks a lot, Dennis. It was really enlightening, very good for the people that don't know it at all. It's a good intro and a lot of questions that gave deep dive. So I think it's was a good mix.
Yeah, probably like a little bit later in several months. I'm working on a more advanced version. Again, that would be generic. As always, I would be using Ignite as a reference platform, but I just have some thoughts on how to introduce a more generic but advanced concepts that apply to not only Ignite but to other distributed memory systems. So hopefully soon I will be happy if you invite me once again.
Thanks a lot. And Chaim, any last words?
Thank you. Good night.
See you all in our next event. Bye.
Thanks a lot.
Ah.
Dennis.
Thank you. Bye bye.